Så, då är det klockan 1 och det är dags för vår tredje installationsföreläsning på temat rymd idag. Så jag vill säga hej och välkomna till er som har varit med hela förmiddagen hittills, så är det ju hej igen. Och för er som är nya så säger jag välkommen till denna installationsföreläsning som professor Kuhn ska hålla i atmosfärsvetenskap, och han får strax prata lite mer själv. Jag tänkte introducera mig själv. Jag heter Lena Abrahamsson och jag är dekan för den tekniska fakulteten på Luleå tekniska universitet. Och för er som inte har varit på en installationsföreläsning tidigare så kan jag berätta att det här är föreläsningar som alla våra nya professorer håller, och de hålls i samband med vår akademiska högtid som nu är på lördag, då de nya professorerna blir installerade. En installationsföreläsning, där får vi lära oss lite grann om grunderna i ämnet. Vad är det här för ämnet? Vad är atmosfärsvetenskap? Får vi lära oss lite grann. Men framförallt får vi lära oss lite grann av forskningsfronten inom en del av ämnet och vad som kommer för typ av forskning. Då är det dags snart att börja, och du ska hålla på ungefär 35-45 minuter, någonting sånt. Det kommer att finnas tid för frågor efteråt. Och titeln på föreläsningen är Snö och ispartiklar i Kiruna och deras roll för jordens klimat. Så, varsågod Thomas.
Tack så mycket Lena. Och välkomna till min installationsföreläsning. Thomas Kuhn heter jag, professor i atmosfärsvetenskap, och jag är mycket intresserad i snö och is i moln över Kiruna. Welcome to my installation lecture. My name is Thomas Kuhn. I'm professor in atmospheric science, new professor in atmospheric science, and I'm very interested in snow and ice ice and clouds above Kiruna. And that's also where I do my research. I work at the Space Campus in Kiruna, one of the satellite campus of LTU outside Luleå. So we'll be talking now about snow and ice. If I can go to the next slide. But before I talk about my measurements and what methods I'm using, I will give a short introductory lecture or give you some background. There is some connection to space. Lena mentioned this is the third talk on space. You can measure these things from space. But what am I measuring? Cirrus. There's a meteorological definition for cirrus clouds. For me and my colleagues, we use a slightly different definition. It's cold clouds that are so cold that they only contain ice. And so we're talking about temperature range from -40 to -70 degrees. And that's the temperature range that you typically find in the upper troposphere. So what is the troposphere? Troposphere is the lowest layer of the atmosphere. Here in Sweden it's between ground and about 11 kilometers. In the tropics it's a little bit higher, up to 13 kilometers. And so in the troposphere, that's where all the weather happens, where the clouds are that contain significant amount of water. And cirrus clouds or ice clouds in particular, they occur quite often. When it's cloudy outside now, low clouds, you may still have above a high layer of cirrus clouds, ice clouds. And they can also happen, or they always are somewhere on the globe, and they can cover large areas around Earth. Then they have certain optical properties, like they're thin, and they can be geometrically thin, but also optically thin. They're translucent. That means they let a lot of the visible light through. And since they are in the upper troposphere, where all the clouds are, they are the first layer of clouds that interacts with incoming sunlight. And the majority of sunlight, or the energy in the sunlight, is in the visible. So they will let most of this light through of the energy, but some of it is reflected. Not much is absorbed, but some of it is reflected, and that is lost back into space. Energy that is not going further down into the Earth atmosphere system. So these clouds actually have a cooling effect. At the same time, they are absorbing, now in a different wavelength range, in the infrared. Infrared is heat radiation. So they absorb part of the heat radiation coming from the surface of the Earth that without clouds would escape unhindered into space. And with clouds, some of this energy is absorbed, some of this is then emitted back down to the surface of the ground, and some of it into space, but less because they are so cold. So they have a warming effect. They keep some of the heat and make that it's warmer even on the surface of the Earth. Cooling, warming, then altogether they have some effect in between, sometimes cooling, sometimes warming. And what exactly it is, that depends on many properties, and not only how thick the cloud is, but also on properties of individual particles in this cloud, how are sizes and shapes distributed. So for the energy balance and for the climate, it is important to know these details on the detailed level. And it is important to do observations that you then can feed into meteorological models. You can do observations, measurements with in situ measurements or remotely. Remotely, that is, for example, with LiDAR, laser beams shining at the cloud, and some of the light is scattered back from cloud particles received by the instrument. But these measurements, they have an advantage. They're from satellite, they're from space. The satellite comes by quite often, and it comes by many places on Earth. But the disadvantage is it's quite far. It's remote, this measurement. It cannot see the details on the microscopic level of these clouds. And actually to get a good product, to get a measurement on the ice cloud from the satellite data, for example, a backscatter from LiDAR, you need to have some knowledge on the microscopic level. You need to do some assumptions, for example, what sizes, what shapes, how they are distributed. And that you can only get through in situ measurements. And you can do in situ measurements. In situ means in place. So you take your instrument into the cloud. You can do this on a balloon or on aircraft. Both platforms have advantages, disadvantages. On the balloon that I'm using, you can get more detailed information. Aircraft is flying faster, you get less details, but you can fly through more clouds. On the other hand, it's also more expensive. We have a lot of in situ data already, and most of it is from aircraft. And most of it is from lower latitudes than the Arctic. It's mid-latitude and tropical measurements. So there's only very few data in the Arctic yet, and only very few detailed balloon data. So it's important to collect more data of this kind. Snow, what is snow? Snow is ice crystals, agglomerates of ice crystals, other ice particles. You can call it cold precipitation. Most of the precipitating particles are frozen. It's anything between heavy snowfall and no snowfall at all. You have small ice crystals floating in the air in ice fog. And even snow is important. It can alter the properties on the ground, become white and reflective. It is a resource for fresh water in the spring. It is important maybe for many of us to get good forecast if it's snowing or not, for road traffic, for aviation, for safety. So again, it's important to do observations. And again, remote measurements have advantages. For example, you can use radar, but you need in situ measurements to get this microscopic detailed information that you also need. So I'm also doing measurements on the ground of snow in Kiruna. To continue my initial lecture a little bit, talk about how are ice particles formed and then how are they growing. You can have, at warmer temperatures, cloud droplets. So you have a liquid droplet. If you cool it sufficiently, you can freeze that droplet. Then it turns into a roundish ice crystal. It doesn't freeze just below zero. You need quite a bit lower temperatures. And you also need, unless you go very low, you need something to start the nucleation process of the crystallization in the droplet, an ice nucleus. You can also form ice crystal directly from the vapor phase, from gas phase. For that, you need an ice nucleus, but then you can, if you have sufficient water vapor, sufficient humidity, you can deposit molecules directly onto this initial nucleus, and then it slowly turns into a crystal. So if you have one of these two, frozen droplet or small ice crystal, you can continue growing them by continue depositing water molecules if there is a sufficient amount of relative humidity. Deposit these molecules, make it grow into a larger crystal. Something that looks like here down in the left corner. And I actually have some samples that you can look at later of such snow crystals. They can grow also by collecting cloud droplets, liquid droplets. I said they don't freeze just below zero, so if you have an ice crystal and cloud droplets at the same time, these cloud droplets, they are super cooled. They're below zero, but they don't turn into ice. But one way to turn them into ice is hitting a frozen surface. That initiates the crystallization. They will turn immediately into ice. They're so small, they maintain their shape. That you see in the middle down there. You see ice crystals with some little frozen droplets on them. And if you haven't seen this on actual snow, you can have a look here later. Then a snow crystal, if it is precipitating, it may collide with other snow crystals, collecting some of them, leading to an agglomeration of crystals, also called snowflake. So now you know that is the difference between snowflake and a snow crystal. Snow crystal is a single crystal, and snowflake an agglomeration of crystals. But I call anything on this slide ice particle usually. So how much water do we need, and how much water is in the air? I said if we have enough, we can grow ice particles, we can grow droplets, or we can form droplets in the first place. But how much water is in the air? We measure that usually with relative humidity. And the relative humidity can be at most around 100%, a little bit more. Why not much more? Because above 100% then we can form droplets. They take up water vapor, the molecules, reduce the concentration, and so bring it back down to around 100%. Relative humidity, what does that mean? It's relative to a reference. That reference is temperature dependent, as we'll see, and that's why it's more convenient to have this relative humidity. It's relative to reference, and the reference is the concentration in equilibrium with liquid water. As you see here in this picture, if you have a surface of liquid water, you always have evaporation. That is molecules leaving the liquid water. They increase the concentration above the liquid water. If you have an increased concentration above there, you get some molecules hitting the liquid water, and some of them make it back into the liquid. That is condensation. If these two processes are in equilibrium, the concentration above the liquid water will not change, and you have the equilibrium concentration of water vapor. I also call this the vapor pressure. So this is the equilibrium vapor pressure. Why pressure? It's convenient to compare it to air pressure. If you take away all the other molecules, only leave water molecules, and leave them to fill the same space that you had before, you would get a certain pressure. And that is the vapor pressure. It's a partial pressure. So, and how much molecules are leaving the liquid water, that is a strong function of temperature. The evaporation is a strong function of temperature. So then the equilibrium vapor pressure is also a strong function of the temperature. And that you can see here on this slide. You see this exponential curve. Every 10 degrees you sort of double the equilibrium vapor pressure. And the curve that you see here, that indicates 100% relative humidity, the purple curve. If you're below that curve, relative humidity is below 100%. Say at 20 degrees, like you see this blue line here, 50% relative humidity, you're halfway down from the line. How can you increase relative humidity if you want to form liquid droplets, for example? One way is not change the concentration, but change the temperature. So if you have 50% relative humidity, your reference is up there. If you change the reference, but not change the concentration, you will change relative humidity. And as a strong function of temperature, it goes quite quickly. So you move to the left on this blue line until you come and cross the equilibrium pressure line. That's 100% relative humidity. That's the dew point. When you form condensation, you move a little bit above it. It's a little bit more than 100%. Another way to get supersaturation or above 100% is if you breathe out humid and moist air, like this green line at the right side. It's moist, it's below 100%, but it's quite high. I breathe that out in the morning when it's moist but cold, but still below 100%. Because mixing is a linear process and the equilibrium vapor pressure is exponential, you end up above 100% in the middle and you get a cloud in front of you when you're exhaling into cold air. I'm more interested in sub-zero temperatures, as you can imagine. So in a second we'll extend this to sub-zero temperatures, but I want to point out 25 degrees as an example. Take that, go to 100%. The equilibrium vapor pressure there, you read, is about 30 hectopascal. Compare that to air pressure of about 1,000 hectopascal. So it's about 3% of the molecules are water molecules. And in terms of mass, that is about, in a cubic meter, you have about 3 grams of gas, of water in the gas phase. If it's 25 degrees and very humid. The colder it gets, the less water you have. And now I'm extending this curve to below zero. And the purple line is still equilibrium vapor pressure with respect to liquid. So the reference is liquid water. Liquid water does not freeze readily. Droplets do not freeze readily below zero, so it makes sense to extend this line. But you can also have ice below 0 degrees Celsius, and ice actually has a different equilibrium vapor pressure. It is lower. It is more difficult. If you think ice is a crystal, it's more difficult to take a molecule from the crystal, from the crystal structure and let it evaporate, which is called sublimation, when it's from solid to gas phase. More difficult means there is less sublimation, and you only need a lower concentration to keep that in equilibrium. So the blue line here, equilibrium vapor pressure with respect to ice, is below the one with respect to liquid water, and that has important consequences. If you form a droplet by increasing relative humidity to above 100%, you form the droplets, they take up water vapor. And as you make it colder, the relative humidity can increase, but the droplets will grow and take up that water vapor. So they will keep the relative humidity close to 100%. So if you move that cloud towards colder temperatures, you will actually follow down on this purple line. If you then, maybe at -10, -15, you start to freeze the first droplet, then that droplet all of a sudden has a different reference. The concentration is still here, 100% with respect to liquid water. Supersaturation with respect to ice. So this one ice crystal can actually grow faster than the droplets. And it takes up water vapor, the relative humidity drops below 100% with respect to liquid water. The droplets don't grow anymore, they actually start to evaporate, and they are a resource of water vapor for the one or few ice crystals to grow. So you can have many ice crystals in this intermediate range between the two lines. It will drop below 100%, it's still above 100% with respect to ice, above the blue line. So you can have mixed phase clouds in this intermediate temperature range. If it becomes much colder, everything is turned into ice. And if you have mixed phase clouds, you can have this, you can have rhyming, this collection of droplets that freeze onto the ice crystal. So now I want to show you some of my measurements, and I start with the method. It is imaging, and here is a very early prototype that I've used. The beauty in Kiruna is it's sort of an outside laboratory. If you have such a prototype, you just put it out and wait for snow to fall. I detect the snow with a laser beam, which you see here in red. If the snow crystals fall in the laser beam, it will scatter light, and I can detect that light and align the laser with the focal plane of an imaging optics. It's essentially a microscope objective that will image then the ice crystal on a CCD sensor. And you see some example pictures that I took with this prototype instrument, and you see some rhymed ice crystal there on the left, for example. And you notice that it's becoming more and more black if it's becoming more and more rhymed and complex. And it would actually look white if you would see it. Remember, I have background illumination in my optical setup. When you look at snow on the ground, it is white because it scatters light that comes from all different directions. I've further developed this instrument by adding a second imaging unit. So now I look at the same falling snow crystal at the same time from two different directions. One is still this looking from the side, a side view. Now I add another one, which you see here on the slide, with a mirror that looks from the top. Not exactly from the top, that's where particles are falling into the instrument, but as much as possible from the top. So I get a much better idea about the shape of these particles, and I have less problems in classifying their shape. If you have only one image, you may have some ambiguity of what shape you actually see. And you can measure fall speed in one view, and you can measure other properties in the other view. And if you measure fall speed by double exposure in the side view, you can measure the size, the cross-section area from the top. That is more relevant for how the crystal is falling. Here I put this instrument on the roof in the space campus and took some pictures with it. You see some examples of view from above, the top view, view from the side below. Most of them, they're not much surprise, but there's this blade in the lower row, the second from the right, that if you only had the side view, you may mistake it for a needle or some long and thin crystal. Here are other examples. Now the side view is double exposed, so that's how I measure fall speed. And there's another example of where you could mistake a shape. You maybe would not have guessed that there is a bullet attached to this stellar crystal, or that is a plate with broad arms. We have collected many thousands snow crystals, snow particle, and analyzed their shape over the last few winters. And a PhD student has updated a classification scheme which now has more than 100 shapes. To make it more convenient for us to do research and look at shape dependence of some of the properties, we've then grouped these into 15 shape groups. And here you see some examples of the shape groups. Kept columns with plates at both ends, or plates or side planes. On the top you see needles. These are thin and long columns. At the very right, this is not a needle, that's the size reference, is 1 millimeter, which you see on each of these pictures. So now we can look at these properties, how they depend on each other, and how they depend on shape. For example, on the left, look at fall speed as a function of size. If you only would take the average, this black line, somewhere in the middle, you would not do justice to most of the shapes. So you want to take into account that different shapes have different fall speeds. We added mass to our properties by estimating mass from the images and from the fall speed. So you can also analyze how fall speed, mass, and the other properties depend on each other, depending on shape. And here they have similar dependencies, but at a given mass, they can have quite different fall speeds. You see fall speed versus mass in the center plot. We have participated in a campaign, or we have invited US colleagues to Kiruna. They brought with them a small radar. So we measured with imaging instruments, which you can see on the left, our DIC, high resolution, another low resolution unit, and on the right, a radar on the space campus, and these imaging instruments very close by. And they found that with the radar measurements that they took, which you see on the slide here, some sort of backscatter information, you can improve the information on the snow, on the falling snow that you get from these measurements by knowing what type of snowfall event you had. Was there liquid associated? Was it small? Was it big? What shapes? And so on. Because those change the properties that the radar can see. Together with the Swedish Meteorological Institute, or Meteorological and Hydrological Institute, we want to put one of our instruments next to one of their new cloud radars, the bigger radar than you've seen on the previous picture. Will be used for cloud research. It will be used for validating a new satellite. Next year we'll see the launch of EarthCare, which will carry a LiDAR and a radar. So we'll put one of our DICs next to their cloud radar. They already have other instruments like this Parzival that you see here on the right, which uses a laser sheet. If precipitating particles fall through the laser sheet, the light is attenuated. From how much it is attenuated, how long, you can get some information on speed and size, but not really detailed, and you don't get any shape information. So we will learn if that is enough, if we put our instrument next to it, and we can definitely help the radar and the cloud research, and with that then also the validation effort for this new satellite. We also want to do more automatic analysis. Shape classification is quite tedious if you do it by hand. We have had a master thesis looking into this, but only using one of the two views that we have of the same particle. Those results already look quite promising, but if you can add the second view, would be great. At the moment we cannot, because most of the times the side view is double exposed to measure fall speed, and some of them they are overlapping, and that it will be very difficult to figure out. It is easier to change the instrument to setup. Then we can also determine fall speed automatically. So now I will talk a little bit also about the balloon measurements. The setup for the snow measurements is on the right. On the left is the setup for the balloon measurements. Now we're not taking images of the snow crystals as they fall by the imaging optics, but we collect them on a tape. And by doing that, we can increase our sampling volume, or we can increase the amount of particles that we can sample by more than 100 times. And that's important if we go to smaller particles in the clouds, and we want to maintain a good image resolution. So we collect them first and then image. And from the images, we get the same information that we get from snow pictures: size, area, shape. We can estimate volume and mass. If we know the sampling volume, we can also determine particle concentration, and with that the size distribution, and properties like the extinction coefficient, how much light is extinct that is going through a cloud. And that is a property that the LiDAR can measure, the remote sensing method. We have been doing many balloon launches during the recent years, and we perform all these balloon launches out from S-range. We received funding from Swedish National Space Agency for that, and we received more funding to do more launches during the next few years, and those together with LiDAR measurements. Here you see typical balloons. On the left a plastic balloon, on the right a small rubber balloon, taking underneath the instrument and taking it up to the cloud, through the cloud. Once it's through the cloud, has done the measurements, we cut the balloon. The balloon continues, but the instrument is coming back to ground on a parachute and is then recovered by helicopter, which is quite easy in Kiruna, apart from the last few meters that some colleague from S-range has to do. That's how the instrument is attached underneath the balloon. It has an inlet and an outlet on the bottom side. So when it's dragged through the cloud, ice crystals in the cloud, in a relative sense, fall in and fall through the instruments. There is a tape inside the instrument, which I think you can see here in this picture where I took the lid off. The air will make it around the tape. Ice crystals will not. They will collide due to their mass and inertia. And the tape is continuously advanced inside the instrument so that you always get a fresh section of the tape exposed to ice crystals, and then immediately inside it is put underneath the imaging optics, and we take the pictures. And then those pictures are stored on an onboard computer, and that's why we are so keen on recovery. So this instrument called BIC, now balloon, the balloon version of the instrument, produces data like this. This is typical data. You look at about 1 millimeter strip of the tape. You see still the whole of the tape on the top, and you see some ice crystals that have landed, collided with the tape that we have collected. For example, this column, which is about 70 micrometer, just below 0.1 millimeter. We can determine the outline of the particles on the tape, and from that determine size parameters, just as we also doing with snow, and cross-sectional area. We can compile then size distributions, how a size is distributed, and do that for certain layers in the cloud. So we can see how these properties change throughout the clouds, how they change as the temperature changes through the cloud. This example, the temperature was decreasing as it generally does, going up. And at the same time, the concentrations were going up and the sizes were reduced. The reference here is now 0.1 millimeter, 100 micrometer. On other days, we got much larger particles. On that day, the temperature was warmer, so then you think, okay, there's a correlation with temperature. But that is misleading. On some days, we had the same temperature, but still different size distribution, different sizes. And eventually found it's more useful to look, instead of looking at the local conditions like temperature, to look at where has the cloud been formed. What were the temperature, what were the conditions at that point? Did it form at a warmer place? So cloud droplets have formed first, and then ice appeared from those droplets. Or did it form at colder temperature and the ice formed directly? And one is called liquid origin, and when it forms at colder temperature, it's called in situ origin. So it makes, it is very useful to classify the clouds, to do a back trajectory analysis of the cloud that you have measured and see what type of origin it is. And we look at shapes, how they change depending on the origin. It's a simpler classification compared to snow, only 5 irregular compact plates, bullet rosettes and columns. And you can look at shape distributions. You can see some clear differences between the two different origin cases of clouds. Here are 2 examples, 2 clouds, one typical liquid origin, one typical in situ origin. You can see typical differences. You see the same after we average over a couple of measurements from each case, so that there is more small and more compact particles for in situ origin, and then you have more columns and bullet rosettes for liquid origin. And at the bottom you also see the sizes are quite different. With that we could publish an update to a size distribution parameterization of the sizes that is an input to weather forecast models, to climate models. And we could show that you can use the same parameterization that you use at lower latitudes if you distinguish between the 2 different origin cases. As you see here, it makes quite a big difference what cloud type you have, not so much what the temperature is. There is some temperature dependence, but it's more on how the cloud has formed. So we have now this growing data set in high resolution images of cirrus ice particles. And we have seen that it's useful to classify the clouds by origin before you do the analysis. And have a particle size distribution that can be used in the Arctic if you use these 2 different cloud types. And publish shape distributions. We are going to improve BIC, collect more data, and do measurements, as I said, together with LiDAR measurements. The LiDAR measurements will be used to validate earth care, and our balloon measurements will be used to help the LiDAR get better ice cloud products. And on this we have a new PhD student starting next week, which is very exciting. So with these few ice particle pictures, I would like to end my talk, and so I can say that great ice crystals grow below 0. Thank you.
Tack så jättemycket för en intressant föreläsning. Innan vi öppnar upp för frågor så ska vi tacka så väldigt mycket och säga att Luleå tekniska universitet är väldigt nöjda och glada över att ha dig som professor, och vi ser fram emot mycket fortsatt forskning. Varsågod.